So our third type of error bounding that we're going to discuss is what's called the Lagrange error bound, or you'll also see it as the Lagrange remainder. This is our broadest in that it works with any of the series that we are discussing, but it also is the most challenging, and it's going to take several times of us visiting it before you start to get a feel for this. Because it looks very much like the alternating series error bound. And remember, that's because I said the alternating series error bound is a special case of this. So this is when we're using a Taylor polynomial to approximate a function centered at A. And that's the only thing we need, is it's for a Taylor polynomial centered at A. We can bound the error, again, by saying that my maximum error is this, by saying the absolute value of the error, and that's supposed to be a less than or equal to, not just a less than, the absolute value of sort of the next term from the Taylor polynomial. The difference is, right here. Notice that that is not the center that's being plugged into the derivative. It's the value that C is whatever is going to make the derivative B have its maximum value. And that's the part that's confusing. Everything else, it's the center, and just like the next term of the Taylor polynomial, but I have to make sure the derivative gets its maximum value. So before we dive into the example here, if you're working with an alternating series, that C is always the center. And I'll be honest with you, most of the time, even if it's a non-alternating series, C will still be the center. But it's not always. So you want to check the center first, but C could be the value that we're approximating the function at. So if my center is at 3, but we're asked to approximate 3.7, maybe my maximum value is at 3.7. It could be the endpoint, one of the endpoints for the interval of convergence. So you've seen we've done a lot of my convergent interval is -1 to 1. Well, maybe instead of the center being 0, my C would be a maximum when x is 1 or -1. Or C could be an unknown value for a derivative that we already know the maximum for. For example, if your derivative is the sine of something, you already know the maximum value of sine is 1. You don't need to know what sine is, because C is what we're plugging into the derivative in order to get the maximum value of that derivative. So if my derivative is sine, I already know its maximum value. I don't need to worry what C is. I just plug in the maximum value for that derivative. So we're going to be looking at an example here where a third-degree Taylor polynomial centered at 3 is used to approximate f of 3.7. And we want to find the maximum error if the graph shown is the portion of the graph for the fourth derivative of x. So remember, for a Taylor series, if I have a center at 0, I'm doing, f of 3 over 0 factorial times x minus 3 to the 0 plus f prime of 3 over 1 factorial x minus 3 to the first plus f double prime of 3 over 2 factorial times x minus 3 to the second plus f triple prime of 3 over 3 factorial times x minus 3 to the third. And here is my approximation. But then my error is based off of using the next term, my fourth derivative of 3 over 3 factorial times x minus 3 to the fourth, and so on for an infinite amount. Well, I can't actually sum up everything, that infinite number of terms left over, so we're going to tweak the first term of the error. So the absolute value of my error is going to be less than or equal to the absolute value of the fourth derivative of something. We use c to represent it, but we just need of something over, oops, that should be 4 factorial. 4 factorial times x minus 3 to the fourth. So I want the derivative part here to be a maximum. I want its maximum value. Whether I know what c is or not doesn't really matter. The goal is I need the maximum value of that derivative. Well, this is where the graph of the fourth derivative comes into play. I can see by looking at the graph, here is my maximum value. So yeah, I can see that the c would be 3. It would be my center. But that's not what I care about. What I care about is the maximum value of the fourth derivative is 6. So I can say that the absolute value of my error is going to be less than or equal to the absolute value of 6 over 4 factorial times x minus 3 to the fourth. But they tell me that this is for when I'm plugging in 3.7 for x. So the absolute value of the error is less than or equal to 6 over 4 factorial times 3.7 minus 3 raised to the fourth. Again, I'm not required to simplify that, but if I did, I would say that the absolute value of my error is less than or equal to 0.060025. So again, even though I have no idea what my approximation is, because while I could find it, it doesn't matter. I can say that my error is less than or equal to 0.06. It's plus or minus 0.060025 away from the actual value.